Okay, so mass is the amount of matter, and that's all I knew. And yet, no one ever asked me, well, is this something you can see? Like, if I look at that thing there, can I see mass? Well, I can see this made of matter, but can I say how much mass it is? And that's something you got to think about. I can't actually see mass. For example, here's something. Here are two objects right here. They both have made of matter. Which one has more mass? But there's something in your brain going on. Something in your brain saying, more, more, more. You know, something is in there, isn't it? Now, you're old enough and you're smart enough to say, don't get tricked. I've been tricked many times before. So which one? Which one has more mass? You say, we don't know. If you're willing to say, I don't know, at least you understand now, you can't actually see mass. What if, though, I had two objects made of the same material and neither one of them were hollow? Nothing was hollowed out. What if I had, what if I had this? Two materials made of this, they're made of the same material. Then can I tell which one has more mass? And the answer is yes. Now, why is that? Why is it that I can't tell you who has more mass there, but here I can? And so there's another word coming in, isn't there? Yes.
They're the same density.
Right, but we're going to get into density too, right? And that's another thing we're going to talk about here, density. And so those objects up there, as a matter of fact, have the same mass. The kit that I bought has like 6 different things in it, and they both have the same mass. And so you say to yourself, well, you're right, I can't see mass, but I can interpret if it's the same material, then I can interpret you have more mass than you do. Another thing that people you're going to find as you get into physics, a lot of times people will say mass and inertia are like this. And I don't think I ever had a teacher that talked to me about inertia at the same time they talk about mass. And inertia, and you've heard this even on commercials, the tendency of an object at rest to do what? To stay at rest. An object in motion to stay in motion, and you'll find out later in another chapter, stay in motion at a constant speed in a straight line. And we'll talk about that later. But so inertia is one of those things where it's like, what is your tendency to stay at rest? And so if we do take this and you say to yourself, well, I know which one has the most mass just because I'm going to interpret it, but what if they were different objects? How could I tell who had more mass? And I might do a little thing like this. I might say, move, 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 move. So which one seemed to have the least tendency to stay put? The smaller one. And so that's one way of doing that. Some people say that mass is a measure of inertia. The more mass you have, the more inertia you have. Now, we'll get into inertia quite a bit in here when we get into physics and stuff like that. But anyway, let's go to this next thing. How about up the definition? How about the SI unit? Even though the metric system used grams, the SI system uses kilograms. So anytime you have a physics equation and it has to do with mass, you have to convert to kilograms. Now, they made that decision because it worked well with everything else. I'll show you, I'll do some other examples today, but, and what kind of instrument would you use? Well, we have this is called a mechanical balance. This is a mechanical balance, and what it does, it simply says if you put the same amount of mass on both sides, then you will balance. Now somebody had to figure out how to electronically do the same thing. Now, this, of course, is going to have to do with these things called forces. We'll get into forces in a minute. But I want to show you this. I think I told you about I don't know how many years ago. Did I say 20? I don't know. Could have been more than 20. all of the science teachers, middle school and high school, they were, did I tell you about this story before? So we had to go to a after-school learning. It was you get credit for it, but the people were specialists, and the only people there were science teachers. And what they were doing is they were trying to say, what are we doing in science? Are we teaching science differently than we teach like history? If you have science and here's your vocabulary words, know the definitions, let's move on to the next chapter. If that's what we're doing, then we're not really teaching science. And so it had to do with reasoning skills. And so I want to show you one that they gave. And these people, give them a lot of credit because they went around the whole country and they took random people in different states, and they took people like in first grade, fourth grade, seventh grade, ninth grade, all the way up to the first year in college. And they gave them a test. Now, if you were young, then they actually brought you into a room. They were nice to you, and I'll show you how they did it to the young people. But if you're older, they would do something like this. So what I'm going to do here, let me cover this up. Okay, and so here was a question. Have I showed this to you before? Tom has 2 balls of clay. They're the same size and shape. When you place them on the balance, they weigh the same. And that's what I did there. I had 2 balls of clay, and I made sure that they weighed exactly the same. And then here's the way they would do it. With older people, they just had it in writing. With younger people, they actually had them in here, and they said, can you see how they're the same? And then they said, I'm going to take this off, and I'm going to do something with this thing. And what they did is they took this clay and made it big, sort of big. They might have done something like this. And then the question was, what do you think is going to happen if I lay this on there? Now remember, you got young people all the way to freshmen in college. And yes, as they got older, more people got this question right. But they didn't all get it right. And as a matter of fact, it was incredible how many people did not get it right when they were younger. And so the idea was, what's going to happen here? Well, your mind has different things that are going on. Your mind says, what did I do to the clay ball? What do you think I did to it? It's flat, isn't it? And so in your mind, there's something in your mind saying something's less. But maybe something in your mind saying what? Something is more. And so it really was interesting to watch the videos of the people saying that. And they even said, well, it's bigger. It's a big pancake. And they said, when I put it on there, it's going to go down. This side's going to go down. And other people said, no, it's not as big. It's not as big. And so if you put it down there, it's going to stay up in the air. And so let's take a look at the answers. And this was actually one of the easier questions, but even though it was one of the easier questions, they actually had numbers of what percent of people were getting this right and what percent not. And it was startling to me to watch, even up through middle school and high school, the percent of people that were missing this question. I also, remember, the only people there were about 80 science teachers there. And we all took this test. When we first got there, I said, what are you talking about? I'm a teacher. You don't give me a test. But we did. We had to take a test when we got there. And this is one of them. And there were 12 questions on this thing called the Galt test. And there were 12 questions. And remember, they're only science teachers. And what do you think the average was on this test? 90?
86.
Out of 12, I didn't do the percentage, but out of 12 questions, the average grade was 7.5. Even though it was over 20 years ago, I clearly remembered that. It's like 7.5. And they actually had a little histogram of how many people got 2 right, 3 right, 4 right, see that? And then you had the average. And it was shocking. It was shocking because I'm sure that a lot of these people are really good science teachers. You give them a book and they can do a good job and present it well, and you know the vocabulary words and all that, but they weren't really teaching the stuff of science that made it science. And so let's take a look at the question again. It's a 2-part question. Which of these statements is true? But then, so you had to answer one of those, but then you had to answer the reason. Why did you say that? If you think it's A, then why? What's your reasoning? All right, take a look at that, and don't worry about it. I think you're going to get it right, but what do you think? Which one's true? A lot of people did think that the clay ball, the flat one, weighed more because it was like big. And then some people said the ball would weigh more because it looked bigger. It looked bigger or taller. And this is really what you're looking for here. A lot of people didn't understand that. If I don't take any clay away and I don't add any clay to it, then what should happen? It should still balance, shouldn't it? So later, when we talk about an astronaut going from the Earth to the moon, I say, what happens to their mass? What happens to an astronaut's mass if you go from here to the space shuttle? Well, let's say International Space Station now, because we're not doing the shuttle. If you go from the Earth to the space station to the moon, what happens to the astronaut's mass? And a lot of people will not give me the correct answer. They will not give me the correct answer. That means that they might have tried to memorize something, but they didn't understand the concept of mass. If I don't chop that astronaut's arm off, or I don't add a backpack to the astronaut, what should the astronaut's mass be on the Earth versus in the space station versus on the moon? What should be the mass? It should be the same. Now that's one of those things you should have down by now. Mass is not going to change unless I add mass or take it away. Is that right? All right. Now, there is something that is going to change, but it's not mass, is it? Well, it's incredible. Like I said, there were some teachers that even missed this question, which I thought was one of the easier questions they had. All right. Another thing we're going to do is, those of you who think this is simple, don't underestimate the Big Six. The Big Six, if you know really well, you'll understand a whole lot more than most people. Here's a situation we have. Do you know how much, excuse me, I forgot. Let's talk about weight. Let's talk about weight. And what do you think about weight? Have you heard about weight and mass? Okay. Well, actually, when you looked it up, what did you have for a definition? Do you remember your definition for weight?
The amount of force gravity pulls on an object.
Okay. And the amount of force that what?
Gravity pulls on an object.
Okay. And what color is gravity? And what does it look like? If I pull on you, you'll know who pulled on you, right? What force? What is gravity? When gravity pulls on me, what does that look like? And we say that, and I've even said it before, the pull of gravity. We like to say that, don't we? But is gravity pulling on you? If there was nothing else in the universe except you, would something be pulling on you? Okay, so now there's nothing else in the universe except you and the Earth, and you're out here. Will the Earth pull on you?
Yeah.
So is the Earth pulling on you or gravity pulling on you? The next question is, are you pulling on the Earth? Okay, so what's interesting is we say the pull of gravity, but it's really the pull of the Earth on the object, isn't it? And you have a pull on the Earth too. We'll talk about that in another chapter, but I have an instrument here that actually will measure pulls and pushes. So if I go down to forces, forces, even though as sophisticated as physics is today, what is the definition for force? Anybody remember the definition? Anybody remember it? It's as sophisticated as physics is today. It still says it's a push or a pull. What is that? Isn't that kind of weird? You know, we have some really high-level physics people, but a force is still considered to be a push or a pull. Well, I have an object here that measures mainly pulls. Yes?
Maybe it's like, a force is something that I forget what the word is, but like it affects an object.
Well, lots of things can affect an object, but see, the word affect, is that any better than the word pull? And you say something affects an object, and it's hard to describe, isn't it? So humans do this all the time. We may not know exactly what it is, but we can tell when it's there. I cannot really tell you what electricity is, not exactly. What is the electricity? Oh, you know, it's like lightning. No, that's not true. Lightning is when electricity goes through the air and excites the air molecules and makes you see the lightning, isn't it? I'm not seeing lightning, I'm actually seeing excited air molecules. So I don't see lightning. What color is lightning? I don't know. Lightning on one planet will be different color than another planet. So I have a little thing that measures pulls like this, and it's called a spring scale. Look at that? And well, in fact, we even have bathroom scales, don't we? Bathroom scales can find your weight. And so it has something to do with a pull, doesn't it? Push or a pull. And so if I were to do this, here's a kilogram, and I'm gonna use a kilogram because that's SI. And we know it's a mass of 1 kilogram, but its weight is measured in newtons. Its weight is measured in newtons, and it's very close to 10. I'm going to use 10 for a while until we do calculations. When we start doing calculations, I'll use 9.8. Now, the question is, wait a minute, 10, 9.8, what kind of units? Newtons. Newton, named for Isaac Newton. And so this is about 10 newtons, isn't it? I want you to remember that. 1 kilogram of mass is 10 newtons, isn't it? So what if I take this into the International Space Station and here, and I go like this, and I put them together, and I say ready, and I let go of it. Then what is the weight going to be there? If I'm in orbit, what's the weight of a 1 kilogram object? On the Earth, the weight of a kilogram object is 10 newtons. What is the weight of a 1 kilogram object in the space station? If I let go of this, it's going to go like this. And what's its weight going to be? 0. It's going to be in what they call a, quote, weightless environment. It's not weightless, it's, quote, weightless environment. Some people call it microgravity. Some people call it 0G. And we'll talk about G here. But this would weigh nothing. But now let's go to the moon, and what would happen on the moon? Would this thing weigh something on the moon?
Yeah.
And how much? What's that number? What is it?
1 or 2, 6.
1 what?
6 newtons.
1/6. Well, 1/6 of 10 newtons, right? If it weighs 10 newtons on the Earth, it'll weigh 1/6 of that on the moon. What's 1/6 of 10 newtons? 1.67, isn't it? Is it 1 point? Yeah, it'll go like this. It'll go down to about there on the moon. Now remember that the mass didn't change because I didn't cut any piece off. I didn't add any. So the mass didn't change, but the weight did, didn't it? Now, what's interesting is we have a situation here where when they started going to space, there was a serious concern. It was, they had figured out that you would be in orbit and you would be in a, quote, weightless environment. And I have another chapter, a whole chapter on this, but I want to show you real quickly what's going on here. It's not really weightless, it's, quote, weightless. And what they're doing is a short story about this. Why are astronauts weightless in space? I promise you, it has nothing to do with the fact that they're about 100 miles away from the Earth's surface. They still weigh a lot there. But they're in a weightless environment because of something else. Yes?
Is it because they're in orbit?
Yes, but what is it about being in orbit that makes you, quote, weightless? Yes?
Well, I would say it does have to do something that they're away from Earth, because instead of the net force being pulled towards the center of the Earth, there is no net force pulling strongly in one direction, but it's like all around them, because they have no huge gravitational pull on them.
What about that big old thing called the Earth? It's only 100 miles away.
It's not as strong when you're orbiting it.
Yeah, because
I want to agree with you that it's not as much of a pull when you're on the surface versus 100 miles. But I will tell you that you still weigh a lot. When you're 100 miles away from the Earth, you still weigh a lot. But why is it that we seem to be a weightless environment? And go ahead.
Because when you're spinning so fast, there's a centrifugal force that pushes you outward, which cancels Earth's weight.
That's a whole other story about can we put in artificial gravity by spinning. That's something different, okay? I'm not going to get into that today, I can make a 1G, if I spin the ship a certain speed, I can make it simulate a 1G atmosphere, meaning you'll kind of feel like you have weight. They even have talked to you about having, in the future, having places where you go halfway into the hub and it's half a G. And they like that idea because maybe like in surgeries and things like that, your organs are kind of like, they're not laying flat, you know? And they could have sports, half G sports, where all of a sudden people can jump tremendously higher. So we could actually play around with how much you weigh in a rotating situation. That's another situation. Now, but this one, I'll give you the short story and then we'll study it in more detail in another chapter. But if I were to go into an elevator and I rate this weighs 10 newtons, and then somehow the cables are cut, and me and the elevator and all of us were to start plummeting toward the earth, what would happen in that elevator? Before I died, I would actually see something which would be kind of unusual. And what I would see is I would see every object accelerating toward the earth, and guess what this thing would weigh? It would weigh nothing. Now, I'm going to die because of my weight, but I'm in a, quote, weightless environment. If I was on bathroom scales and the cables were cut, I would weigh nothing, but I'm going to die because of my weight. Are you with me? So, so imagine an astronaut. You say, well, what are the astronauts? Are they falling toward the earth? Yes. But they're moving this way very fast. And so they move very fast this way, and they're falling toward the earth. So if the earth weren't here, they would go this way, away from the earth. But because they fall, they go this way. And they go this way, and they go this way. And that makes them go this way. Now, if you can get the right speed for that distance, they can fall away from a straight line. They can fall away from where they would have been, and they will fall toward the earth, but they won't get any closer to the earth. And they will be in orbit. And they would have that feeling of like an amusement rides, where you're in what they call free fall. And so in a, quote, weightless environment, they had trouble because they said, we need to know about our astronauts' health. Are astronauts killing themselves being in a microgravity environment? And so how do we know? Well, you know, on Earth, if you're losing weight, we know there's something wrong. So how do we do that? And say, well, it's easy. We just make a balance like here and put this on the International Space Station, and we just weigh them like that. What do you think about that? Will that work? And the reason I know you're going to underestimate these 6 words. I know you're going to underestimate them, but it's really, don't really understand them as well as you think you do. Why can't I make a mechanical balance and put that on the International Space Shuttle, on the space station, and say, let's weigh you every day. You sit over there, you sit over here, and I'll put the standard masses over here, and I'll find out how much you weigh. What do you think? Why not? Yes?
For that balance to work, it needs to have normal gravity.
I do. It's a mechanical balance, and it only measures mass. It doesn't measure weight. But I need a gravitational field to make that happen, don't I? And I don't have it. So if I had this in the space shuttle or in the space station, I would sit there and I'd put things on there and it would do whatever. It would not weigh anything. So this brings me back to a story. This takes me way back. My son, who's 42 years old, he liked science, and he liked space, and I was good. I thought, oh, who knows, you know? And so what happened is he wanted to do an experiment, and I still have this book. This book is like really old. And so he wanted to do a science fair experiment, but what did he want to do? And so this is from an astronaut, and you can see how it's really torn, but when he would go and give tours of different schools, kids would always ask lots of questions. And so he said, you know what, I'm going to write a book and which has 100 of the most frequently asked questions, and I'm going to answer them in a book. And you can buy the book. See that? So maybe I won't visit your school, but you can read what I have here. Now, the reason he titled this is that what was the number one question that was most asked all around the country? How do you go to the bathroom in space? Now, that is a very good question, and it's in here. And even though I can tell you that real quickly, they do have a toilet. They do have a toilet, and it can be anywhere. It doesn't matter where it's at. I don't know if you're thinking it has to be on the floor. No, they're in orbit. Everything's a floor, everything's a ceiling, isn't there? There's really no up and down. So let's say the toilet's over here on the wall. You push yourself over there, you float over to the toilet, and you strap yourself in. It's very, very important. You flip this switch, which is a fan, and once the fan is going, then you can let it go. Okay? And anyway, they kind of take care of everything, put it in a package, and then on Earth, they'll take care of it when you get back. Yes?
How do you sleep?
How do you what?
Sleep.
They have bags, and they may be different now. It's kind of like a hammock, and you just kind of strap yourself in, and you can be anywhere you want. You can have the hammock this way or that way or like that. And the main thing is not to fall out of bed and go somewhere else. So you just kind of strap yourself in a little hammock like that. Now, the reason I want to show this to you is that, and even though I won't show this to you today, but I will tomorrow, this is phase one. This is type 1. How do you weigh an astronaut in space? If you're in a, quote, weightless environment, and I need to know how much you weigh, how can I weigh you in a weightless environment? And they said, we have to know. We have to know if the astronauts are losing weight. Well, they're weightless. How we'll never know. Well, let's think about this. Weight and mass on the Earth are directly proportional. What does that mean? If you have twice the mass, you have twice the what? If you have twice the mass, the Earth will pull on you twice as hard. You get that? And that's why people like to interchange those words, because they're directly proportional, aren't they? So, if we can find your mass, then we can eventually convert that into weight, can I? Is it true that 1 kilogram is 10 newtons of weight? So I could convert it. If I can find your mass, I could convert that to weight, couldn't I? But how do you find the mass of an object? And so what we have here is an equal device, and this is a kind of like what we did, my son and I. We did not this nice of a version. I'll tell you how we did it after we do this one, but excuse me. What we did is, and he did us all. I mean, we did it together. He did every one of the measurements. He did the averaging. He even drew the graph. And back then, I think I told you, that's when science fair projects, the judge actually talked to you for at least 15 minutes. Not today. Today's science fair, oh, look at that one. That looks good. Oh, look at that color. Okay. You can know nothing about that project and sometimes get a blue ribbon. And it wasn't that way before. The judge would talk to you. If you didn't know about your project, they knew that your parents did or something like that. You get that? So what we did is we had a really long metal ruler, and I clamped it to a table, and then what we did was we taped pennies onto it. 5 pennies, 10 pennies, 15, 20, 25, and then we put them on there, and we would pull it back and let it go, and watch it go like this. And so I'll show you how, this is sort of how they weigh an astronaut in space. He's sitting in a seat, but the seat actually is on springs. It's on springs, and the seat can actually go this way, or some of them went this way. And tomorrow I'll show you on YouTube the new version of it, which is kind of weird, but let me show you how this works. All right, there's a mass of 1 unit of mass, okay? Wait, I'm gonna pick it up. All right, see this thing here? I'm gonna pull it back, and we wanna know how long does it take to take 10 trips. I hereby declare, my operational definition is a trip is all the way there and back. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 9, stop. Okay, and that's a hard one to measure. But why, it didn't take very long, did it? it didn't take very long to take 10 trips, did it? Just that. Okay, so what? What does this have to do with anything? And they would have done the same thing with this. And by the way, I'll give you the name of it. This is called an inertial balance. An inertial balance. You see, if I can find your inertia, I know your mass. If I know your mass, I can find your weight. And so let's put a thing in here. Let's put a mass in here and say, okay, now you take 10 trips. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Was that a shorter amount of time or a longer period of time? Now, why? Because these are like springs, all right, in a way, they're flat blades. When I got it going this way, what tendency did it have to keep going that way? More than before. And so then the spring says, come on back. No. Come on back. No. Okay. And it starts coming back this way. All right, go this way. No. No. Okay? I had a tendency to keep going this way. So what would happen then if I took this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, why does it take longer? Because it has more mass, it has more inertia, it has more tendency, if it's in motion, to keep moving. The springs want to bring you back, but you have more mass, it takes longer before you come back. Now if I put the third one in there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so imagine you build this inertial balance and you have nobody in it, and you go ahead and let it go shake. You shake it and find out how long it takes to take whatever, 10 trips or whatever. And then you have some standard masses or standard weights. Hey, let's put 40 pounds in there. Oh, it takes longer. Hey, let's put 80 pounds in there. Let's put 120, let's put 160, let's put 200. And then make a standard curve. A standard curve means I use a standard to produce a graph. And what can you do with a graph? You found out last chapter. What can you turn a graph into? A mathematical what? Equation, right? And if you do that, you can put that in a computer program. And then what you do is, you ask the astronauts to get on there, strap themselves in. They had to kind of make themselves in a tight ball because they said their organs would shift inside their body. So they had to kind of be like a tight ball. And you shake them. And so you shake them and say, hey, you know what? Today, you took the same amount of time for 10 trips as 182 pounds. I got that from my formula. You must weigh 182 pounds today. Even though they can't weigh the astronaut, they could find his inertia, which is his mass, and then convert that into weight. And I think that's really neat that they, if you just understood this, the big six by definition wise, you would have never figured out, hey, how am I going to weigh these astronauts? I don't know. But we can't. But we can't. Somebody understood what the idea of mass and inertia was there. All right. All right, let me go ahead and, oops. I'm going to go to one more today. One more of these Galt things, and I'm going to let you think about this. Okay, are you ready? I'm going to read it for you, and then you have these options. It says here, Lynn has 2 jars. They are the same size and shape. Each is filled with the same amount of water. She also has 2 metal weights of the same volume. One is light, and the other one's heavy. Light, heavy. She lowers the light weight into jar 1. The water level in the jar rises and looks like this. So it went from 6 up to 10. Is that right? Now, she said, if the heavy weight is lowered in a jar 2, what will happen? So I want you to think about this. You don't have to say it out loud. What do you think your answer is going to be? And then what is your reasoning? All right, let's take about 15 seconds. What is your answer? And what is your reasoning? All right, everybody got it? This question, many more science teachers miss this one than, as a matter of fact, college. Yes, young kids miss it. They miss a lot of these. Even middle school miss it, high school miss it, and even college, quite a few people miss this because in your brain's saying there's more of something, isn't there? And you want to say that the water level is going to go higher. But the question is, and you did a lab on this, what is it that displaces water? What property of an object displaces water? Does the color of the object displace water? The smell of the object? Does the mass of an object displace water? Ooh. Does the weight of an object displace water? Does the volume of an object displace water? And that's what it is. So what's going to happen is a lot of people miss this question because they know it weighs more, doesn't it? But the volume is the same. The volume is the same. And so what property displaces water? Volume. All right, what's the answer here? C, and what's your reasoning? They're the same size, aren't they? And size, I can see volume, can I? I can see volume. All right. Anyway, what we'll do is tomorrow we'll go ahead and try to finish the big six, and then we'll get into ratio concepts. And like I said, we have it's like a 80-point, whatever you want to call it, a mini test or a big quiz. And I'll even talk about that a little bit more before we get there. Hey. Okay, thanks. Wait, the time change, it's an hour. You had to move the clocks the other way an hour. Did you move it? Okay, all right.